The story of the jet engine begins with a simple, breathtaking idea. Air, compressed and ignited, becoming pure thrust. Nothing has reshaped global mobility, trade, and modern warfare more profoundly. The jet engine did not just make travel faster, it collapsed continents, rewrote geopolitics, reshaped tourism into a trillion-dollar force, and underpinned the global supply chains of the 21st century. A machine that once lived in the margins of theory now carries more than 4 billion passengers each year. This episode tells the story of that machine, how it was imagined, engineered, manufactured, perfected, monetized, and ultimately turned into one of the most complex industrial products ever created, the modern turbofan. It starts with the roar of a machine spinning at 10,000 revolutions per minute, swallowing air with the appetite of a hungry planet. A commercial jet engine inhales half a ton of air every second. Temperatures inside the combustion chamber exceed the melting point of the metals that form it. The turbine blades at the core endure forces equal to holding a truck at the tip of a fingernail. And they do all this for tens of thousands of flight hours without failing. This is not engineering. This is controlled insanity made routine. The jet engine represents the very frontier where physics, metallurgy, precision machining, and market economics collide. A frontier where every millimeter matters and every gram of fuel has consequences measured in billions. To understand why the jet engine mattered, consider the world before it. For most of human history, speed was limited by the strength of muscle, the pull of wind, or the burn of coal. The piston engine pushed boundaries, but it was always fighting air as much as using it. At high altitude and high speed, pistons became loud, inefficient, and unreliable. Aircraft designers knew it. If humanity wanted to break past the 600 km/h barrier, the propeller would eventually become the bottleneck. Two men saw past that bottleneck. In Britain, a young RAF cadet named Frank Whittle wrote a thesis in 1928 arguing for engines that used exhaust gases to create thrust. The idea was radical. Instead of pushing air backward with a propeller, why not accelerate air through a controlled explosion and let Newton's laws do the work? Whittle's early engines were temperamental, loud, and frightening. But they worked. Across the world, in Germany, Hans von Ohain pursued the same idea independently. By 1939, his engine powered the Heinkel He 178, the world's first jet-powered aircraft. Two visions on two continents racing toward the same breakthrough. It wasn't merely convergence, it was inevitability. A jet engine is, conceptually, simple. Air enters, gets compressed, mixed with fuel, ignited and expelled at high velocity. This is the Brayton cycle, an elegant marriage of thermodynamics and combustion. In practice, nothing is simple. Modern engines contain thousands of precision machined components. Their core includes three key systems. 1. The compressor. Rows of rotating blades squeeze incoming air to pressures up to 40 times atmospheric level. 2. The combustor. Fuel injects into the compressed air and ignites at temperatures of about 1,700 degrees C. 3. The turbine. Blades extract energy from the hot gas to power the compressor, and the remaining energy becomes thrust. Wrapped around this is the fan, the signature of the turbofan era. These fans can exceed 3 meters in diameter, the size of a small house, yet must be balanced with the precision of a surgeon's hand. The engineering mantra is simple: stronger, lighter, hotter. Every improvement is a war against physics. Higher temperatures increase efficiency, but melt metals. Higher pressures increase thrust, but risk catastrophic failure. Larger fans reduce fuel burn, but add weight and complexity. This tension drives innovation. It is why the jet engine industry became a proving ground for metallurgy, CFD simulation, 5-axis, CNC cutting, ceramic coatings, additive manufacturing, and digital monitoring systems. Jet engines are machines that have forced entire industries to improve or disappear. Jet engines are not just engineering marvels, they are business ecosystems. The industry is dominated by three giants: General Electric, GE Aerospace, Rolls-Royce, Pratt and Whitney. Each company invests billions in R&D for engines that may take a decade to design and certify. A single engine program, like GE's GEE9X or Rolls-Royce's Trent series, can exceed $10 billion in development cost. But here's the secret. The profit is not in selling the engine, it's in maintaining it. Engines are sold at or below production cost to aircraft manufacturers. The real business is the power-by-the-hour model, long-term service contracts in which airlines pay for every hour an engine operates. This model generates steady cash flow for decades. A modern turbofan may bring $15–30 million in purchase price, $40–50 million in lifetime service revenue. The engine becomes an annuity, a flying subscription service. It's one of the most lucrative models ever devised in industrial capitalism. The first jet engines arrived on the battlefield. Speed gave advantage. Altitude meant safety. Jet fighters such as the Messerschmitt Me 262 and later the F-86 Sabre proved the concept. But the true revolution was civilian. After World War II, governments realized that air travel could shape economies. Jet engines enabled flights over oceans without stops. They created mass tourism. They connected supply chains. They shrank the world from a place measured in weeks to one measured in hours. The Boeing 707 and later the 747 powered by jet engines were not just aircraft. They were socio-economic events. They allowed cities like Dubai, Singapore, and Hong Kong to emerge as global hubs. They made international business travel routine. They made fresh flowers from Kenya appear in Frankfurt and smartphones built in China arrive overnight in Europe. Jet engines rewrote geography. To understand why jet engines are so extraordinary, consider the forces inside them. Temperatures. The hottest parts reach 1,700 C, far above metal melting points. Turbine blades survive only because of ceramic thermal barriers and internal cooling channels thinner than hairs. RPM. The turbine spins at 10,000–20,000 RPM. Fan blades, sometimes 3 meters long, must endure enormous centripetal forces. A single fan blade can cost more than a luxury car. Fuel efficiency. Modern engines burn 30–40% less fuel than engines of the 1980s. The savings for a major airline run into hundreds of millions annually. Safety. Jet engines fail less than 1 in 100,000 flight hours. They must keep running at full thrust even when ingesting birds, hail, and volcanic ash, though the last one remains a threat. Manufacturing. A single blade may require 3D woven composite structures, single crystal superalloys, and investment casting techniques perfected over decades. Jet engines are machines with personalities, demanding, temperamental, and utterly unforgiving of mistakes. The jet engine market is a study in high barriers, high risk, and high reward. Only a handful of nations can produce them: the US, the UK, France, Russia, and now China. A fully certified commercial jet engine is among the most geopolitically sensitive technologies on Earth. 3 factors shape the market. Certification. Getting an engine approved requires tens of thousands of test hours and rigorous regulatory reviews. A failure late in development can cost billions. Supply chain depth. A jet engine contains up to 40,000 parts from hundreds of specialized suppliers. Disruption in a single foundry or CNC shop can delay an entire aircraft program. Long product cycles. Engines stay in service for decades. Airlines want reliability and predictable costs. Manufacturers want long-term service revenue. The result is an industry where reputation is capital. A single failure can destroy market share. The machines powering modern aircraft also shape national economies. Airbus and Boeing exist only because engine makers exist. Without engines, their airframes are shells. Developing countries depend on jet engines for tourism, trade, emergency aid, and medical logistics. The market for air travel grows strongest in Asia and Africa, regions where rising incomes create demand for mobility. Every time a new airport opens in a developing nation, a jet engine indirectly drives local entrepreneurship, hotels, logistics companies, exporters, and more. The jet engine is not just hardware, it is a development engine. 3 trends define the modern jet engine era. Ultra-high bypass turbofans. Engines like the GE9X and Rolls-Royce Ultrafan push fan diameter to new limits. More bypass ratio means more thrust from cold, slow air, dramatically improving efficiency. Composite materials. Carbon fiber fan blades and casings reduce weight while maintaining strength. Ceramic matrix composites survive temperatures that kill metals. Digital twins. Real-time engine data is continuously transmitted to manufacturers. AI models predict wear, optimize maintenance intervals, and reduce downtime. Engine manufacturers now operate less like hardware producers and more like software-led analytics companies. The jet engine's greatest strength is also its weakness, which is its precision. Three major pressures shape the industry. Safety standards. Engines must achieve near-zero tolerance for error. Even a hairline crack can lead to disaster. Environmental pressure. Aviation contributes about 2–3% of global CO2 emissions. Engine makers race to reduce fuel burn and adapt to new fuels. Supply chain fragility. COVID-19 revealed vulnerabilities. Casting houses, CNC suppliers, and specialty material manufacturers are bottlenecks. Building a jet engine is like conducting a symphony where every musician must be perfect. Hydrogen combustion engines aim to eliminate carbon emissions. Hybrid electric systems add batteries and electric boosters to improve efficiency on takeoff. Open rotor architectures may return propeller-like engines, but with jet-level performance. Adaptive cycle engines, now tested by GE and Pratt Whitney, alter airflow patterns mid-flight like a bird adjusting its wings. Each development brings new engineering puzzles, but also new business opportunities. Nations that dominate the next generation of jet engines will shape global aviation for half a century. The jet engine is the most consequential machine built by human hands. It turned the sky from a barrier into a highway. It connected families, economies, and cultures. It made possible everything from global logistics to space exploration. In a world obsessed with digital technology, it is easy to forget that every global supply chain still relies on two very physical forces: air compressed and fuel ignited. A jet engine is more than thrust. It is a promise of connection, of possibility, of worlds once distant becoming reachable. In the story of machines that changed the world, few deserve the title more than this one. And the sky, still open and wide, is nowhere near finished with it.